All right, so you are, this is my Chem 19 version of Electron Configuration, so it's going to be very brief. If you're looking for the better explanation of electron configuration, check out the Chem 2A video, but this is the, for Chemistry 19. We don't get quite as deep into electron configuration as the Chem 2A class or the Chem 10 class. So just really briefly, why are electrons important? Well, the difference between a blimp, like a Hindenburg, blowing up and a blimp, like a modern blimp, not blowing up, is the difference of 1 electron. Because Hindenburg was made of hydrogen, and the modern blimp is made of this element, which is what? Can you look at it and tell? This is helium. And yes, it has differences of protons and neutrons, but the electrons on the outside of the atom are really what make the differences in behavior, in reactivity. And there's a big difference here because hydrogen is on top of group number 1. It's not a metal, but it's in the same group as the alkali metals. And helium is a noble gas. And so it behaves differently because it has a full electron configuration. So what does that mean, electron configuration? Well, we know about electrons because Bohr, Niels Bohr, that Bohr model of an electron, he did a few experiments. So just kind of walking through what he did, he said he saw that different elements produce different colors, and if you separate those colors through a prism, you get this differentiating light pattern. So what could cause these different, colors to show up on different elements? So we first need to understand what is causing these colors in the first place. And so you excite these elements and we get these different color patterns. So for example, like a neon light or hydrogen would show us a different pattern if we separated the light through a prism. And this is actually how we tell how old stars are. We see the light from the star, we can differentiate it with a prism, and then if it's a lot of hydrogen, it's a young star. If it's a lot of heavier elements, it's an older star. So what does this have to do with anything with electrons? So electromagnetic radiation, including visible light, comes in waves and as particles. And electrons also behave as waves and as particles. And so if you have a certain energy that is being given off, it corresponds to a certain wavelength in a certain color or in a certain type of energy. So like microwaves are lower energy than visible light. So if you're looking on this chart, your lower energy is radio and your higher energy is gamma. And you can kind of see how the waves change as you move through that. So visible light is higher energy than microwaves or infrared. All this 5G stuff, that's all microwaves. So it's actually lower energy than just heat energy that you give off with your body right now, or visible light that we used to see. So Bohr was able to kind of put this together. He was able to say, well, I see these colors coming off of these elements, and I know that electromagnetic radiation or visible light has to do with the energy and the wavelength. So therefore, the electrons, something must be creating waves. So how could I create waves in water, right? I have to move. So my electrons are moving around inside my atom because they're excited, they're getting heated up by electricity, or they're getting heated up in a flame, and they're releasing energy as waves in certain colors. So the electrons must be in certain energy levels. So he came up with this idea of these energy levels, or these orbits of electrons kind of floating around the nucleus. And so energy is absorbed and the electron moves up in energy, and then the electron moves back down and the energy is released in a certain color or wavelength. So looking at this image, we have the electron moving up away, and then when the electron moves back down, the energy is released. Take a second and think about, why does the electron move back down? Just the big hint in this image. The electron is a negative charge and the protons in the nucleus are positive. So the electron moves back down because it is attracted to the nucleus. And so we call this bottom state, ground state, and we call the electron in the higher energy level excited state. And so electrons always will move from excited back down because they want to be closer to the nucleus. And when they do that, they release energy. So it's like if I give you a lot of energy and you get up and you start doing a lot of stuff, eventually you're going to get tired and you're going to sit on your couch or your chair and you're going to go, ah, and you're going to release some of that energy, right? The electrons are doing the same thing. And so really looking at this hydrogen spectrum, I can see that some electrons are moving not very far, giving a low energy red, and some electrons are moving out really far and giving high energy violet. And so referring back to the electromagnetic spectrum in a previous slide, you can kind of see the difference in their wavelengths and energies here. But this is essentially what Bohr did. So he came up with this, the Bohr model that we see here on the right, with N being your energy level. So higher energy, farther away from the nucleus. Bohr's model is great. We still actually use it for a lot of things. We've kind of discovered that electrons don't just kind of move around the nucleus in like an orbit like planets are on the sun. Electrons are actually really weird, and we don't actually know exactly where they are. It's more of a statistical probability that an electron is in a certain area. Kind of like, you know, if you're thinking about, if you're a sports fan, baseball statistics. So statistically, where will the ball land up in the strike zone or not? You know, there's a lot of factors that go into it, but it's still, this is a probability map of where that ball will go. And so what we're going to look at in just a second are not images of really where electrons are, but they're probability maps of where electrons might be. And so we have these different shapes. So all I want y'all to know is what the different shapes are and how many electrons you can put in these shapes. So we're going to go back into my slides so that I can do a little writing. So an S shape is a spherical shape. As you see here, there's one shape per energy level. You can fit 2 electrons in each shape. So I can fit 2 electrons in each of these spheres. So that means if I have one shape, I can fit 2 electrons max in an S statistical region. So this probability map is for S. This is the energy level. So this is saying, okay, the first energy level, here's the statistical probability of the electron being in this S shape. Next energy level, probably in this shape. Next energy level, probably in this shape. Okay, so just one of these is really one example of 1S. The next shape is called P, and it's more of this dumbbell shape. There are 3 shapes per energy. Oh, sorry. This starts at energy level 1. So it starts at energy level 1. So there's 3 shapes per energy level. And here we're starting at energy level 2. So we're kind of going to be building on, so starting with an S, then another S and adding a P, and then in third energy level, we're going to add another shape. Starting at energy level 2, N equals 2, energy level 2. So 2 electrons per shape again, for a total of 6 electrons. So here are your individuals, and then you have combined P's over here. I'm not going to ask you to draw these or know these shapes, like know what they are. I'm just going to ask you to just, when I'm going to tell you in a minute SPDF stuff, and I want you to know where that comes from, so you're not like, wait, what are these letters? The letters are just tell me what shape it is. So D shapes, there are 5 shapes per energy level. And it begins at energy level, starts at N equals 3, energy level 3. 2 electrons per shape for a total of 10 electrons max you can put in every d orbital. And you've got kind of this combination of p orbitals with this one that's like got a little hula hoop around it. These are just maps of where electrons might be. And then we have F. So there are 7 shapes per energy level. Again, I'm not going to have you draw any of these, so don't be afraid of that. We start at energy level 4. N equals 4. We have 2 electrons per shape. So there's 14 electrons max you can put in an f orbital. Here's kind of what you need to know. You need to know energy level 1 holds 2 electrons, okay? Because it has 1 s. Energy level 2 holds 8. Energy level 3 holds 18. Energy level 4 holds 32. That's a really kind of what I need you to know. And so you don't need to get too much more detailed into the, splitting it apart into SPD or anything, but that's essentially where we need to go with it. And then I'm going to show you how to use the periodic table to kind of figure out, if I give you a configuration of electrons, you can identify the element, and that's it. I'm not going to have you write full electron configurations. So you have different blocks. If you want to decorate one periodic table with this, you can, but you have your S block. So these electrons, the last electrons in these elements, they go into that spherical S shape. The last electrons for these elements, they go into one of those like dumbbell shapes. The last electrons in these elements, they go into that like more complicated shape, and these are just really crazy down here. So you got your S, P, D, and F blocks, and you can actually kind of think about these and use them as a guide. Like, there are 2 electrons in every S shape, so if you look at how thick this block is, it's only 2 squares thick, so that can give you a little bit of information about it. Like 6 electrons fit in a P, 1, 2, 3, 4, 5, 6, 10 for D, and 14 for F. Like, you don't have to memorize some of this stuff. What am I going to ask you to do? So these are electron configurations. I'm not asking you to write them. They tell you the kind of energy level and the shape and number of electrons in that shape. So all I'm going to ask you is something like this. Tell which elements belong to these arrangements, okay? So how do I do this? I'm going to do the first one and then ask you to do the other 2. So looking at this, A, 1s2, 2s2, 2p6, 3s2, this kind of looks like gibberish. All you need is the last piece, 3s2. What this means to me is this is the second element in the 3s. So let's go to the periodic table here. Look at our period numbers, 1, 2, 3. And I know this is the S block. So the second element in the third S is 1, 2 is magnesium. So this is magnesium. Can you try the other 2? So looking at your last one for B, 2p4. So let's go up here. We're going to go to the second energy. I highly recommend in your periodic tables, the ones you're coloring and writing on, that you number the right side as well. Second energy, P block, 4th element, 1, 2, 3, 4, oxygen. Okay, let's do this next one, 3p3. Just look at the very end. You can, if you want to go through the whole thing, you can, but all we need is 3p3. So 3p, 1, 2, 3, that's phosphorus. So here's some electron configurations, abbreviated. Notice that the D does something weird. It goes back in energy level. I'm not even going to ask you about that, so don't even worry. All you have to know is up to calcium. Abbreviated just means that what you do is you put the noble gas before that element in brackets, just to kind of say like, hey, I don't want to go all the way from hydrogen. Just say like, hey, if I want to get to calcium, just like, hey, remember the last time we were like super stable in noble gas configuration? Oh yeah, that was argon. Start there, and then 4s1, 4s2. But I'm not going to ask you to write the configurations. It's just for you to have a reference of what am I talking about. Again, you do not need to know any of these D blocks here if you are in Chem 19. We got plenty of other stuff to learn in Chem 19, so don't you worry.